In this video, I will be solving problems using the gas laws obtained in the previous video. So let's just, for a quick reminder, boils, then we have Charles, then we have Guy-Lussac, then we have the combined gas law, and finally Avogadro's. So let's separate this. Okay, we said that for boil, the temperature and the moles are constant, so we would have pressure 1 times volume 1 is equal to pressure 2 times volume 2. For Charles, the pressure and the moles are constant, so it only deals with the volume and the temperature. Volume 1 is over temperature 1 is equal to volume 2 over temperature 2. Guy-Lussac had number of moles and volume constant, so it deals with pressure and temperature. So pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. The combined gas law, you could think of it as a combination between the Boyle's and the Guy-Lussac law. So P1 V1 over T1 P2 V2 over T2. So the only thing that we don't have are the number of moles, and we said that they are only variable in Avogadro's law. So I mean, if you look at Boyle's law and Guy-Lussac's, you only have to add the temperature as the denominator in Boyle's law to obtain the combined gas law. So now we said that Avogadro's is the one that the only one that has the number of moles in the equation, and the pressure and the temperature are constant. So we'll have volume over moles of the first sample, volume 2 over moles of the second sample. And those are the 5 equations that we'll be using today. I'll be coming back to this page just when you have your variables, or when they give you the values. If you look at all the equations, you can see which you have, so which one you will use. You'll understand it better as I do it. So let's go to the first problem. So 1. And this problem says that we have a sample of an ideal gas that occupies a volume of 68.1 centimeters cubed. So V1 is 68.1 centimeters cubed. It also is at 945 torr, so the pressure 1 is 945 torr. And it's at a temperature of 18 degrees Celsius. So our temperature 1 is 18 degrees Celsius. Gas. What volume would the gas occupy at 118 degrees Celsius and 745 torr? So they're telling us the P2 is 745 torr, and that the temperature 2 is 118 degrees Celsius. So that will only leave us with volume 2, which is what they're asking. Now let's go back to our equation. We have volume, pressure, and temperature. So the only equation that has volume, pressure, and temperature in it is the combined gas law. So that's the equation we'll use. P1 times V1 over T1 is equal to P2 times V2 over T2. So let's write it. P1 over V1. P1 is equal to P2 times V2 over T2. But first, let's check the units. Now, if this was the ideal gas law, you'll want to convert the volume into liters, the pressure into atmospheres, and the temperature into Kelvin. However, if you think about it, the torrs and the pressure will go with the torrs, so they won't matter. And we'll get the volume in centimeters cubed, but something you'll always want to do, always, in every problem, is you'll want to convert the degrees Celsius into Kelvin. you cannot use Kelvin. You cannot use Celsius in any calculation for gases. It will change as we study more chemistry. But for gases, you'll always want to use the absolute temperature, which is Kelvin. So converting this, we'll get 291.15 Kelvin, because it's simply adding 18 plus 273.15 and 391.15 Kelvin. So our units are fine now. Now let's solve for the V2, which is what we want in this equation. So V2 would be equal to, we still have P1 times V1. Now the temperature will be multiplying as it goes like this, and the T1 is still down there, and the P2 is here. So you plug in the values, and I get 116.1 centimeters cubed. You could change this into liters, but if the problem doesn't ask you to, you could say this is the answer. But always remember that the degrees Celsius have to be converted into Kelvin. In this, if it was the ideal gas law, you would have to change it to liters, atmosphere, and Kelvin. But that's in the ideal gas law. So now let's solve another problem. So this problem says a sample of an ideal gas has a volume of 128 centimeters cubed. So let's say that is our V1. 128 centimeters cubed. And it's at minus 20 degrees Celsius. Temperature 1. 20 degrees Celsius. To what temperature must the gas be heated at constant pressure if the found volume is to be 214 centimeters cubed? So they're telling us the volume 2 is 214 centimeters cubed. And they're asking to what temperature it must be heated for it to reach that volume. So T2. Now let's go back and see which equation has V1 and T1, or volume and temperature as their variables. So we have the Charles law. It has V1 over T1 is equal to V2 over T2. So let's write that here. V1 over T1 is equal to V2 over T2. Let me fix that too. It doesn't look like a 2 at all. Okay. Now, the first thing you'll want to do is to check your units. So the centimeters cubed will go with each other because the volumes will divide, so that doesn't matter for now. But the degrees Celsius have to be changed into Kelvin, so there's a minus here, so be careful about that. By adding 273.15, sorry, I get 253.15 Kelvin. So just plug in the values now. But let's first solve for T2, which is a variable. So it'll pass multiplying, and the V2 here times T1 over T2, right? V1, sorry. V1. So you simply plug in the values, so it'll be 214 centimeters cubed times 253.15 Kelvin over 128 centimeters cubed. That gives us a temperature of 423 Kelvin. And that is the temperature at which the gas will reach 214 centimeters cubed. Now let's do another problem. This problem states that a 12.2 liter sample, so let me write 3 here. They're telling us the volume first. Volume 1 is 12.2 liters, containing 0.50 moles of oxygen gas. So we have the number of moles 1, 0.50 moles of O2 at 1 atmosphere. So they're giving us the pressure is 1 atmosphere and the temperature is 25 degrees Celsius. if all of this oxygen is converted to ozone, which would be going from O2 to O3, and let's balance this real quickly, so it'll be like that. It'll be 6 on each side. So I'm going to read it again. If all of this oxygen is converted to ozone at the same temperature and pressure, what will the volume of ozone be? So they're asking us for V2. Now, there's a key sentence here that you have to pay attention to. I'm going to read it again. If all of this oxygen is converted to ozone at the same temperature and pressure, what will the volume of ozone be? So at the same temperature and pressure. That's telling us already that this section here will be constant. So there's only one equation that has the number of moles as a variable, and that is Avogadro's law. And Avogadro's law says that, let me go there real quickly, V1 over N1 is equal to V2 over N2. So let's go back. Let's write that down. V1 over N1 is equal to V2 over N2. We have the volume 1, we have the number of moles 1, we're looking for the volume 2, we're only missing the number of moles of the ozone, which is our second sample. So you could say that 2 is O3 and 1 is O2. So by simple stoichiometry, using the mole diagram, we can obtain the number of moles. So let's do that. We have, let me erase this part. We have 0.50 moles of oxygen, right? And we have our chemical reaction here already balanced, so that's good. So we'll say that, well, 3 moles of oxygen form 2 moles of ozone. And as you can see, this cancel out, leaving us the moles of ozone, which would be 0.33 moles of O3. Now let's plug in the values in the equation. But first solve for V2, so V2 would be equal to V1 N2 over N1. And so V1 is 12.2 liters times the 0.33 over 0.50. So that will give us about 8.1 liters of ozone. And that is how you solve a problem using Avogadro's law. Now, do not be tricked if in a problem they tell you the values of the pressure and the temperature. That does not mean that you have to use them. You really have to read what the problem says. If you didn't read that it said that if all of the oxygen is converted into ozone at the same temperature and pressure, you wouldn't know that these values are constant, and you wouldn't know that you would have to use the Avogadro's law. So always be careful about what the problem says. Read every sentence. Do not just use every value they give you. And well, that is how the gas law problems go. You could try using Boyle's law, and I think it was Guy-Lussac's law that I didn't do, but they use the same logic.